Okay, it is a great pleasure to introduce Klaus Kröncke from KTH Stockholm, and he will talk about on the volume-renormalized mass. Thank you very much, Klaus.
Okay, thank you very much for the introduction. It's a great pleasure to speak at this Geometry with Symmetry seminar, and I hope this talk is going to be interesting for you, even though it's maybe a bit out of the scope, the main scope of this seminar, because there are not so many symmetries, maybe directly, but I think it's a topic of general interest. So this is kind of an overview talk, a report on a quantity we found like, let's say 2-3 years ago, and we started over the last couple of years, and I'm going to give an overview of the work that has been done so far. So this is an overview on papers that I did jointly with Mattias Dahl, also KTH McCormick, also in Sweden, Luleå, and former postdocs of mine, Alan Pinoy, Francesca Oronzio, and a current postdoc, Louis Yudowitz. And as a motivation for the definition of our quantity, I'm first going to do a brief recap on the other mass quantities. There's something I can't go to the next slide for some reason. No. Okay. So let us recall what the ADM mass was for asymptotic Euclidean manifolds. So you take a manifold that is asymptotic Euclidean. That means it's asymptotically to our n, the Euclidean metric. In the sense, you should think of some manifold that looks like this. So there might be some topology inside. But if you go far outside and if you remove a compact set, then a manifold looks at least topological like Rn without a ball. And the metric at infinity is going to approach more and more the Euclidean metric. And then you take an integral over the boundary over a ball, which you can think as this sitting somewhere here. That's the boundary of your ball. And then you let this radius go to infinity. And what you integrate over that ball is the divergence of the metric or the push forward of the metric if you use an identification like diffeomorphism phi minus the differential of the trace also of this metric, and you insert the unit normal vector. And then you take this quantity, and the question is, what can I do with it? Well, there's the theorem by Martin Crucial saying if the metric G decays sufficiently fast towards the Euclidean metric, namely of this rate r to the minus n over minus 2 over 2, and a little bit faster to subtract an epsilon, then this following quantity is finite. It's this normalized version of the scalar curvature. So you take the integral of the scalar curvature over a ball, and then you subtract that integral we have here. And this linear combination you let go to infinity. And it turns out that under these conditions, this integral or this combination is finite. And then in particular, if the scalar curvature itself is integrable, then this ADM mass, which is defined as the limit of this integral over the boundary of a ball, is well defined. So it's a finite quantity and it's coordinate invariant. And this is what is interpreted in the physics world as the mass of the isolated gravitational system. This is modulated by this asymptotic Euclidean manifolds. So you think of some matter that is lying around and distributed over, let's say, a compact subset of manifold, a matter that generates some curvatures and topology, and then outside, however, where the matter, if you're far away from the matter content, you manifold and the metric gets flatter and flatter. And I'm going also to present a proof of this theorem because it's a motivation for what we're going to study next. So let's go and prove this thing. And then you will also see how this mass quantity, how this boundary integral pops up. Let's assume for simplicity here that our coordinate or diffeomorphism phi is just the identity. That's not the existence of this diffeomorphism is not really crucial. It's one can adjust the proof. But for simplicity, like take the identity here. We fix a reference metric, it's called G hat, the Euclidean metric, and we take as H the difference from G and the reference metric, the Euclidean metric. And then what we do is we linearize the scalar curvature, or we tail expand the scalar curvature. So then you get scalar curvature of G, is the scalar curvature to the background, plus the linearization in the direction of the difference, plus an error term, which is somewhat a Lagrange rest term of second order. Now we know what the linearization of scalar curvature is. It's given by this divergence of G with respect to G hat of divergence minus the gradient of the trace. And then there's a scalar product of the Ricci tensor of the background. But now, of course, our manifold is Euclidean metric, so there's the Ricci tensor, and you're left, and the scalar curvature is also 0. So you're left with an error term that's quadratic in the perturbation H, and a divergence. And now you already see what is going to happen, because you take the divergence exactly of the expression that was defined in the ADM mass. So now you integrate or BR of the ball, and then you just use Stokes. And then the boundary term that pops up will be exactly the boundary term that is defining the ADM mass. So then you an arc with infinity, and you get exactly the result that I presented. And of course, we know for the ADM mass, there are positive mass theorems. So I'm going to present it shortly. There's theorem by Shin and Yao. There's like an older version from 79, which works for dimensions up to 7. And then there's a proof of a couple of years ago, which also works in high dimensions. Then there is also the spin proof, spin proof by Witten. And the statement basically says, well, if the scalar curvature is non-negative, which is interpreted in physics well as non-negative energy density, then this ADM mass is also non-negative. And it's 0 if and only if your manifold is isometric to Euclidean space. So that's a very short recap on the ADM mass. Now there's another mass quantity, and that's actually a vectorial quantity. So now you take a manifold that is asymptotically hyperbolic space, not the Euclidean space. We take a different background now. And you think of hyperbolic space as sitting in Rn plus 1 with the Minkowski metric. So hyperbolic space can be embedded in Minkowski space. And then, again, you take a metric that is asymptotically hyperbolic metric. You take, because of the hyperbolic world, exponential decay assumptions. So you take e to the minus n over 2 plus a little epsilon. And then you want the scalar curvature minus the scalar curvature of that background, which is minus n times n minus 1, is in L1 in the weighted sense. So you have to multiply with an exponential factor. And then there's the following quantity, which is well defined. It's a vectorial quantity. So you're integrating some Rn plus 1 valid 1 form of the boundary of a large ball. And this defines a vector that is the hyperbolic mass vector. And there's a similar argument here. So you expand the scalar curvature minus the scalar curvature of the background. But now this time you weight with a vector valid function. And this vector valid function is from the embedding I was mentioning before. So if you take Minkowski metric or Minkowski space, then the hyperbolic space sits in Minkowski space like this. And then, of course, you have the position vector field on Minkowski space, and basically restrict this position vector field to the hyperbolic space. And this gives you this x arrow. So you take this difference of the scalar curvature minus scalar curvature of the background, you weight it with the x, the position vector field, and then you can again linearize the scalar curvature, and then you get the linearization plus an error term. And then for the first term, that happens in the second equality, you can do an integration by parts. So you take the formal adjoint of the linearization scalar curvature that falls on the position vector field, and then the difference is a divergence. And this divergence, or this one form that appears in the divergence, is exactly the one form that appears in this integral above. It looks quite similar to the ADM mass for asymptotically Euclidean spaces, but there is an additional contribution. I don't write it down in details, but I mention it later on if you want. So, and then of course there's also an error term. And then as a feature of hyperbolic space, what happens is that this components of the position vector field are in the kernel of this adjoint of the normalization, so the drop, and you're left with a divergence plus an error term again, where the error term is weighted with the position vector field x, and then you integrate again over BR, and you use Stowe's theorem, and you let the radius go to infinity. And maybe I should add as a comment, you see the diff, again, you assume scalar culture, but the thing is integrable, but you have another weight here, e to the r, and this is coming from this position vector field because the components of the position vector field grow exponentially. And so you have to compensate that, grow exponentially in the hyperbolic if you restrict to hyperbolic space. Okay, so that is the hyperbolic mass vector, and there's also a hyperbolic mass theorem, positive mass theorem presented by Kröncke and Hertzler, which is for spin manifolds. So they were able to modify this Witten proof, which originally has been done for the ADMS. And it says, well, if the scalar curvature is larger than the scalar curvature of the background, again interpreted as non-negative energy density, then this ADMS vector is future-directed causal and equal to 0 if and only if of hyperbolic space. And now basically, I perhaps should have not erased this picture from before, but let me just repeat it again. So there was, so we have a light cone. This is the set of all the vectors in light cone have speed less than light. And future-directed causal basically means it's this vector that you get is in the interior or at the boundary of this light cone. Yeah, and 0 is often if and only if you're isometric to hyperbolic space. Okay, some remark. As an essential ingredient I mentioned before already, is that this position vector field is in the kernel of the adjoint of the linearization scalar curvature. And as a consequence of the positive mass theorem, you get the scalar curvature treated of hyperbolic space. That means you can't increase the scalar curvature per perturbation of hyperbolic space on a compact subset because this would violate the equality case of the positive mass theorem. And also similarly, already in the asymptotic Euclidean setting, or more generally ALE setting, asymptotic local Euclidean, the positive mass theorem for the ADM mass implies a scalar curvature rigidity for certain Ricci flat metrics, because again, you can't make the scalar curvature positive in the interior, but deform the metric because this would be a violation to the positive mass theorem. And in a sense, what we want to do now is we want to analyze more general negative Einstein metrics from a mass perspective. So you want to cook up a mass which reflects those properties we had for hyperbolic space and Euclidean space, but now for general Einstein metrics. And for those, and that's the crucial point here, this kernel of the adjoint linearization will be 0 in general. And so you can only expect scalar curvature rigidity if you assume a volume constraint. That means if you assume the perturbation preserves the volume of the manifold. So you need to work with a different quantity. And this is the quantity I'm going to talk about in this talk. Before, let me just introduce the geometric setting we're working on. It's namely the setting of asymptotically hyperbolic manifolds. So for this asymptotic hyperbolic manifold setting, we need to introduce manifolds of boundary. So you have a manifold boundary, and this boundary is assumed to be compact, and there's some interior. And now you look at metrics that are so-called conformally compact. So that means you have a metric in the interior, and this metric is called CK alpha, conformally compact. If there is a function rho, so that if I multiply the metric G, the function rho squared, then I get metric B, which can be extended on the boundary. And this rho is a boundary defining function, so it has the feature that is positive in interior and vanishes exactly on the boundary, and the differential is also non-vanishing on the boundary. And then you have a quantity naturally induced on the boundary that's called the conformal boundary. Thing is here that, well, the assumption is if you have the match G, it's conformally compact if after multiplying with a boundary defining function squared, you get a metric extends to the boundary, but your boundary metric may depend on a choice of the boundary defining function. But every other choice of a different boundary defining function gives you a conformal metric, and that's why the conformal boundary is a well-defined quantity given a conformal compact metric. So this is the well-defined induced structure on the boundary. It's the conformal boundary of the manifold. For a couple of facts, well, at infinity, so the boundary you should think of as infinity. At the boundary, the sectional curvature goes to minus the differential of the boundary function squared. If you go to 0, that means if you go towards the boundary. And therefore, you call a manifold that is conformally compact, asymptotic, and hyperbolic if the differential has norm 1 on the whole boundary, because that, as you see, means that the sectional curvature goes to minus 1. So it's a very natural definition of asymptotic and hyperbolic. Any questions up to now? Okay, no questions. So why is the setting interesting for us? As said, we're going to study negative Einstein metrics. Well, the thing is, there are many Einstein metrics of negative Ricci curvature on the asymptotic hyperbolic setting. The most prominent one is just hyperbolic space itself. Written in the Poincaré disk model, you see exactly why it's conformally compact, because it's just a conformal factor times the Euclidean metric. And this conformal factor is just the negative square of a boundary defining function. The boundary defining function is 1 minus norm x squared divided by 2. And so 1 over that gives exactly a relation between a hyperbolic and a Euclidean metric. And naturally, the conformal boundary you get is the conformal boundary of the round sphere, because it's the boundary that is induced by the conformal class of the Euclidean metric. But there are many other asymptotic hyperbolic metrics whose Ricci curvature is exactly minus n times minus 1 times the metric. You get it, for example, perturbation. So there's this famous result by Graham and Lee that if you perturb the conformal boundary of the sphere for sufficiently small perturbations, you will always get a Poincaré-Einstein filling. So there's locally near the hyperbolic metric, there is a 1-to-1 correspondence between Poincaré-Einstein metrics and the conformal boundaries. Whereas you can say conformal boundaries parameterize the Poincaré-Einstein metrics. So really, man, it's an infinite dimensional family. And there is even more. In fact, every smooth conformal class on a compact manifold is the conformal boundary of an in general incomplete Poincaré-Einstein metric. So in this case, you can think of, well, there is somehow a conformal boundary somewhere. You fix a conformal class, and then you can solve the Einstein equation in a whole neighborhood of it. And this is what Gaussian says. So you have many in general incomplete Poincaré-Einstein metrics. And it's a very hard problem to try to find complete fillings. But we're not going to touch this problem. It's a completely different one. It's a very hard problem and it's not going to attacked by us. It's a different perspective that we discussed today. Yeah, just a brief remark. If you have a boundary defined function, you can think of minus the logarithm of rho as being kind of the distance function to a fixed point on the manifold. That's just a side remark, because we're going to now use our function regularly. Okay, and I think now I'm ready to define, no, not almost, we are almost ready. Just another definition that is nice and interesting for us. That's the one of asymptotic Poincaré-Einstein metrics. So first, let me explain what it means that two asymptotic hyperbolic manifolds are asymptotic to each other. That means if you take a diffeomorphism that identifies the two manifolds with each other, and diffeomorphism needs only to be defined at infinity, then the difference of the metrics decays sufficiently fast. And by this, I mean that you have some exponential decay with some rate delta. That means, or the order. So you want decay e to the minus delta r. And there is a very convenient feature of the Einstein condition that plays a role here. Let's say if you have asymmetric conformal boundaries and both metrics satisfy the property that the Ricci tensor plus a multiple of the metric decays sufficiently fast. So the Poincaré-Einstein condition, or the Einstein condition, is satisfied up to certain order towards the boundary, you also call that asymptotically Poincaré-Einstein of order delta, then the two manifolds are already asymptotic to each other. So in what is going to follow, we are basically studying asymptotic Poincaré-Einstein metrics. So we demand some condition on the Ricci tensor that is independent of the choice of the reference metric, so to speak. So you can think of M hat and G hat as being some reference metric. But in general, you demand this condition on the Ricci curvature, and by demanding that, you kind of fix a certain class of manifolds that are conformally compact. And these are certain class of metrics that are all asymptotic to each other. And the reason of that is the Pfeffer-Graham expansion. Because you can basically expand a conformally compact metric like this. So you have up to the conformal factor, you have the rho squared plus a family of Riemann metrics in the boundary, and then you can basically just Taylor expand this. And then you have some highest order term, and then some error. And it turns out that all these sigmas, they Riemann, or this sigma 0 is a metric on a boundary. The other sigmas are just tensors, and they are all determined by the Einstein condition. So if you fix sigma 0, then all the next sigmas are determined by sigma 0. That means if you assume this APE condition, then a certain number of Taylor terms in this expansion have to agree with each other. And this gives somehow this, this gives this feature that they are also asymptotic to each other, because you're just looking at certain class of metrics that have this expansion, if you want. Okay, now I'm ready to define our mass quantity, and it's defined as follows. So you take a background metric, M hat, G hat, and you take a metric Mg that is asymptotic to the background metric. And then you have two expressions. The first one is the one that is similar to the one of the ADM mass in the asymptotic Euclidean setting. I mean, formally it's exactly the same expression, just on a different manifold. So again, you take divergence with respect to the background metric minus gradient of the trace, contracted with the unit normal, a certain radius. And then you have another contribution that is in the volume or one ball of the metric G minus the volume of the metric G hat. So these two quantities are interesting now. And we take this particular linear combination, we take this boundary integral to find the ADM mass, plus 2 times m minus 1, this renormalized volume. So you take 2 times m minus 1, this difference of the volumes, and then you take this linear combination, and then they take the limit r to infinity. And this quantity is called the volume-renormalized mass, and brackets should say of the metric G with respect to the reference metric G hat. Okay, so now for the remainder of the talk, I will try to convince you that this quantity is somewhat interesting. And of course, I should explain why exactly this particular linear combination. And as you will see, it shows up in a very natural way. But first a remark. So if the rate is sufficiently fast, then the boundary integral would drop. So then you only have the difference of two volumes. So the volume-renormalized mass is then just 2 times m minus 1, the difference of the volumes in a certain sense. And in a sense, for that reason, you can regard our volume-renormalized mass as a generalization of the renormalized volume to metrics of lower decay, if you want. Okay, so now here is the first analog of a theorem we had at the beginning of the talk in the asymptotic Euclidean setting. So we take two asymptotically Poincaré-Einstein manifolds of order delta larger than n minus 1. So this delta larger than n minus 1 over 2 will show up very naturally. And I will tell you on the next slide why. Again, we have asymmetric conformal boundaries so that they are asymptotic to each other of exactly the rate n minus 1 over 2. And then you also assume that the scalar curvature of the metric is integral in the right setting. So if you add the appropriate constant, it's in L1. So there's the one of the background. You assume that the one of the background is plus n times n minus 1. This is a brief typo here. Then this following expression here, the integral of the scalar curvature plus the scalar curvature background minus the two terms defining the volume-renormalized mass. This linear combination of three terms converges to a real number as r goes to infinity. And in particular, this means if the scalar curvature of the matrix G plus the scalar curvature times n plus constant n times n minus 1 is n of 1, then its volume-renormalized mass is a real number. So it's the exact analog of what we had before for asymptotically Euclidean manifolds. And this functional that we cooked up there, that we call the renormalized Einstein-Hilbert action. It has exactly the right variation of formula. It appears to be constant for dimension 2. And in high dimensions, the critical points of this action are exactly the Poincaré-Einstein matrix. So this is exactly the right normalization of the Einstein-Hilbert action here. And in a sense, a motivation for defining the volume-renormalized mass is as well as the right terms you just need to subtract here that you need to normalize the Einstein-Hilbert action with, that you get some of the right Einstein-Hilbert action in asymptotic hyperbolic setting. Okay, let's prove this theorem now. And then you will somehow see this proof will give you the motivation for the definition if you want. Again, we assume for simplicity, phi is the identity, and let H be the difference of the matrix G with the magic of the background. Again, we do tail expansion. So we take the scalar curvature, and this is the scalar curvature of the reference matrix G hat. Then again, I have this divergence term here. But now you have this term that showed up before, but in asymptotically Euclidean setting, this was just 0. And then you have the error term here again. And you can think of it as being sort of the trace. This has to be something like the trace, because the Ricci of G hat should be at infinity something like a multiple of the magic. So you get something like the trace of H times an error, and this is the term you have to compensate. And it turns out, well, the volume is exactly right ingredient for compensating, because the first variation of the volume is just a trace. So you see here, there's the tail expansion of the volume element, the volume element of G, it's the volume element of G hat, plus 1 or 2 times the trace of H with respect to G hat, plus the error term. And now you combine these two expressions. Well, as I mentioned before, right, the Ricci of G hat is not 0 anymore as in the Euclidean setting, but it is some term which reflects some of the asymptotically Poincaré-Einstein condition minus n minus 1 times the trace of H. See, and this is the trace that will show also that shows up in the linearization of volume element. So now you just need to take the right combination. And this is what you get. The scalar curvature of G plus n times n minus 1 minus the divergence term that I subtracted minus 2 times n minus 1, the difference of the volume elements, is the scalar curvature of the reference plus this background constant n times n minus 1 minus this Ricci curvature term, the asymptotically Poincaré-Einstein term, if you want, scalar product of H, plus O of H squared. So again, an error term. And then again, if you integrate over the ball and let the radius go to infinity, then you get the result. And the decay assumptions that I had, the decay assumptions on the scalar curvature G hat, the asymptotically Poincaré-Einstein condition, that all make the terms on the right-hand side integrable. And that's why all that works. So you see, the reason why I take this linear combination I mentioned before is because that's the way the volume, that's some of the right combination for the volume and the scalar curvature such that you get a divergence term. And such that they can do integration by parts. Any questions? Okay, so, and then I should also mention, there's a generic condition. I will not discuss this so much in detail. A generic condition that shows you also that the volume-renormalized mass is independent of the choice of diffeomorphism phi, because it's something what you want, of course, in order to really call it a geometric quantity. You want to be independent of the diffeomorphism at infinity. Good. Now let's go to some positive mass theorems. Because once you have a mass, or once you think there's something that looks like a mass, you also want to prove positive mass theorems. And so here's a little on what we have so far. We take an APE surface, a two-dimensional asymptotically Poincaré manifold, which is asymptotic to a hyperbolic metric. But now I also take a generalization of the hyperbolic metric and allow such angles. So you allow a conical singularity of a certain angle at the origin. And this way I get this particular family here of background metrics, where I rescale the circle coordinate by a certain factor to create that conical angle. And then turns out, well, if you evaluate that renormalized Einstein-Hilbert action, remember that the left-hand side, I mentioned this earlier, the left-hand side is constant in dimension 2. So this smells very much like there should be some kind of Gauss-Bonnet argument. And this is actually what turned out to be some of the thing to prove this identity. This is more or less a little exercise in applying the Gauss-Bonnet theorem and glue metrics correctly in a nice way. So this renormalized Einstein-Hilbert action is equal to 4 pi times the other characteristic of the one-point compactification of M minus 2 plus an angular contribution. So you get 2 times 2 pi minus omega. And in particular, what you get is that if the scalar curvature plus 2 is an L1 and non-negative, you get the volume-renormalized mass of G with respect to G hat plus some angular contribution is exactly the integral of the scalar curvature plus 2 plus this topological term, which is 4 pi times 2 minus the other characteristic of the one-point compactification. And now, of course, the first term here on the right-hand side is non-negative because of the assumption of scalar curvature. The second term is just a general thing that, well, the sphere has the largest other characteristic. This is exactly why. Both terms are non-negative, and so the sum is non-negative. So that gives you kind of a two-dimensional positive mass theorem. And there's an exact analog of this also in the asymptotically Euclidean setting, where you look at metric two-dimensional surfaces asymptotic to cones. It's the precise analog of that result in the asymptotic Euclidean setting. Right, so that was 2 dimensions. Now we go 1 dimension higher, and in our paper we proved that this year we were able to establish a 3-dimensional positive mass theorem. Now you take a 3-dimensional asymptotic hyperbolic manifold, which in addition is orientable. You take the right decay assumption, which is a delta being larger than 1. Then you assume the scalar curvature is larger than the one of hyperbolic space, so larger than -6. And you also make a topological assumption here. That is, the second homology class, the integer coefficients, does not contain any spherical classes. And under that assumption, the volume-renormalized mass of G with respect to the hyperbolic metric is non-negative. Inequality holds if and only if the metric is asymmetric to the hyperbolic metric. So this is exactly our positive mass theorem in dimension 3, despite this additional topological assumption, which I explained briefly why it shows up. So how do we prove this here? I give you a very brief sketch of the proof and some comments on it. Well, the proof uses a monotonicity formula along level sets of a fundamental solution U to the Laplace equation, centered at some arbitrary point. So you have the manifold here that is asymptotic hyperbolic. We fix a point. That's your P. And if you want, think of the graph of the fundamental solution, and it looks somehow like this. It goes all the way to infinity, close to P. And so you have such kind of level sets. And then you go all the way down to 0 at infinity. And for the level sets, as you change the value of the level, you'll have some monotonicity. And the condition on the second homology class asserts more or less an equivalent way of phrasing this condition is that at first in the composition, there is no S2 times S1 factor. All other factors, all other 7 model geometries are allowed, just no S2 crosses 1 factor, because you always want the level sets to be connected. And the reason for that is Gascoigne formally. You want that the level sets have all characteristics smaller than 2. So you're not allowed to have 2 spheres, because then all characteristic would be twice of that of the sphere. And that would break the monotonicity. You really need connected level sets for applying this monotonicity argument, for getting the monotonicity. And the motivation for trying this ansatz was a similar method, an analogous proof that has been used to reprove the positive mass theorem for 3-dimensional asymptotically Euclidean manifolds with the normal ADM mass. And we figured it's maybe a test to see if our quantity is reasonable and if we can apply the proof if there's a transition of that proof to our quantity. And our quantity was used to prove really a proper positive mass theorem for 3 dimensions. And that's what it is on this slide. And now there's some other things I want to talk about. There's a connection to the Ricci flow. This is something I also want to mention. And what is the connection to the Ricci flow? Well, we're actually able to construct a functional for asymptotic hyperbolic manifolds. And this functional has some interesting properties, namely this functional is increasing under the normalized Ricci flow. That means you take the Ricci flow equation, derivative of the metric equal minus 2 times the Ricci tensor, but then you add a normalization term, which corresponds to rescaling and which makes Poincaré isometrics being exactly the stationary points of this flow. So this function is increasing, and the critical points are exactly Poincaré Einstein manifolds. And then we have a very interesting equivalence, because it turned out, well, a Poincaré Einstein manifold is a local maximum of this entropy if and only if the positive mass theorem holds for all nearby metrics. That means for all nearby metrics near to the Poincaré Einstein manifold that have larger scaling curvature, you also have a larger mass. So you can also say, well, you want that your Poincaré Einstein metric is local minimizer of the mass. It's a different way of phrasing it. Local minimizers of the mass are local maximizers of the entropy. And this is very interesting from the viewpoint of dynamical system, because you have a quantity that is increasing on a normalized Ricci flow. You have a Poincaré Einstein metric that is a local maximum. So it's very smells like this Poincaré Einstein manifold should be an attractor of the Ricci flow. But it also takes some work to really prove it. And this is what I did with Louis Yudowitz. The theorem tells you, well, a local maximum of the entropy is exactly an attractor of the Ricci flow. So you have a local maximum if and only if you have dynamical stability on the Ricci flow. And it doesn't hold if it's not a local maximum, it's dynamically unstable on the Ricci flow. And if you put those things together, it basically tells you that dynamical stability is equivalent to a local positive mass theorem, and dynamical instability is equivalent to a violation of the positive mass theorem for nearby metrics. So that's a way to phrase that. And there are actually similar but less explicit results in the ELE case. So they are a bit less complete. There's not exactly this complete equivalence that I had here, but there are some couple of assertions that go in the direction. And this work in the ELE setting was a motivation for studying the Ricci flow, find an analog in the asymptotic hyperbolic setting. And actually the study of the asymptotic hyperbolic setting, this is where some of this mass quantity came from. So originally we were actually somehow trying to find nice criteria for the dynamical stability of Poincaré Einstein manifolds. That meant first trying to find an entropy, and some of these mass just popped up during the process of finding the entropy. And then all this other stuff came as a result of it. But this Ricci flow question was the starting point of it, if you want. So there's a relation to Ricci flow as an asymptotic Euclidean setting. And finally, you may ask, is there some physical interpretation? A physical interpretation that seeks for somehow Hamiltonian formulation in the context of GR. And I will not maybe talk too much about it, but give some brief comments on that. So as we've seen, there's some analogies between the volume-renormalized mass and the ADM mass. And somehow, if you want to see it purely as a geometric quantity, then it shares some analogies with the ADM mass, but is it a mass somehow in a physical sense? Or is it, as I indicated before, is it just a generalization of the renormalized volume and ADM mass modification as it's written there? And for showing, or for somehow indicating that there is a physical explanation, you want to somehow seek for a Hamiltonian formulation of the Einstein equations, because this is where the other mass quantities explained at the beginning came from. And so we were inspired by a paper of Fisher and Moncrief, who did that in a compact setting, and they found a reduced Hamiltonian formulation for Einstein's equation in a compact setting, and the quantity they cooked up is essentially some kind of volume. And turned out, well, this work can be generalized to our setting. But before, let me just mention two static spacetimes, which serve as the ground state for the other as the mass quantities we were looking at. So the ADM mass appears in the form of Hamiltonian formalism for spacetimes that are asymptotically in Minkowski place, which is minus the t-squared times the Euclidean plus the Euclidean metric. And this hyperbolic mass vector, also explained before, that appears in Hamiltonian formalism for spacetimes asymptotically to the anti-de Sitter space. And the anti-de Sitter space is this metric where you have minus cosh of r squared, the t squared, plus the hyperbolic metric. And r is, again, just the radial coordinate on the hyperbolic space. So now what we want to look at is, want to see if there is a spacetime and background spacetime for our mass. And this is what I'm going to discuss now. There is some. So if you have a Milne-like, if you have a Poincaré-Einstein manifold, then you can build an orientable symmetric. It's an expanding orientable symmetric, so it's not static anymore, but it's expanding. And this is essentially the Lorentzian cone over a Poincaré-Einstein manifold. So you take minus the t squared plus t squared times g hat. So this is kind of a cone, but in front of the t squared there's a minus because you want the metric to be Lorentzian. And a straightforward computation shows that this metric is rigid flat, so it's actually a vacuum solution of the Einstein equation. And then, in particular, well, you can take hyperbolic space, for instance. In hyperbolic space, this cone that they build is also rigid flat, and it's actually completely flat, and it's just a light cone in Minkowski space. So let's do the picture for a third time. Here is this light cone, and then you have this hyperbolic space sitting inside, but then you take proper rescaling of these hyperbolic spaces, and the family of rescalings will fill the entire interior of this light cone. And this gives you the metric of the light cone represented in those coordinates through this, well, this foliation of hyperbolic spaces. And you can, so what I've shown here, well, you can generalize this, then this won't be a light cone anymore in Minkowski space, but it's a more general thing. And each time slice, which is corresponding to one of these hyperbolic spaces, has constant mean curvature, tau, which is equal to minus n times n minus 1. So you have a family of slices representing the spacetime at a certain time. And this family of spaces at a certain time have constant mean curvature, and the mean curvature is also increasing in time. Right, let me erase that part here. And then what we're looking at are rigid flat spacetimes that are asymptotic, such a Milne-like spacetime. So think of the perturbation of Milne-like spacetime. And now assume you have a foliation through its manifolds that have constant mean curvature, exactly the same ones of the background. So you have the background and you have some metric asymptotic to it, and it has the CMC side versus, and this somehow leads to a proper identification of your rigid flat spacetime you're looking at and your background. And then what we showed that in this framework, the volume-renormalized mass of the induced metric on the slices properly rescale is, so to speak, the reduced Hamiltonian of the Einstein-Hilbert action. So now I was presented it as kind of a black box. I didn't go to the details, what a reduced Hamiltonian actually is, and I spared the details a little. But what is essential here and what is interesting is that this mass quantity is actually non-increasing along this foliation, and it's constant if and only if you have such a Milne-like spacetime. If and only if this function n here is equal to 1, and the method G is actually a family of rescaled Poincaré Einstein metrics. So this shows this monotonicity, even if we don't know about the reduced Hamiltonian formulation, this monotonicity shows you that it's somehow relevant for Ricci flat spacetimes of that form. Okay, so now nearing the end of my talk, and I want to come up with some concluding remarks and some open questions. As I indicated before, there was an analogous result of Fishman-Crieve for the spatially compact case where you just have the volume instead of this renormalized volume, because then there is no boundary term. So there is a Hamiltonian formulation of the compact case, and that was somehow the thing where we thought, okay, we can generalize this maybe to our setting. This is what we tried, what we did. And also the interesting thing, one would in general expect a Hamiltonian to be constant along solutions of the associated Lagrangian. Conservation of energy, you would expect that the mass is constant, doesn't change. In our case, however, it's monotone, it's just what comes out of the mathematics. And we would just formulate it that way, well, the monotonicity comes from the expansion, because our background model is an expanding model in contrast to the other models for the other masses that have been discussed before, for which you have static spacetimes. The open questions are, well, I presented some positive mass theorems in dimension 2 and 3. Some first, yeah, this is also from the physics perspective. Is there a momentum version of the volume-renormalized mass? The second one are the positive mass theorems in higher dimensions, and are the Penrose type inequalities, even generalizing some Penrose inequalities in the asymptotically clearance setting. And then a question I was asking myself, is the local positive mass theorem that I mentioned in the Ricci flow context equivalent to the nonlinear stability of this Milne-like spacetime of the background model that is Ricci flat? So here the question is, you have a background model, a Lorentz background model. It's a solution of the Einstein equation. It solves the initial value problem. The question is what happens on the perturbation of the initial data? Do you converge back? So this is a different kind of stability than in the Ricci flow case, but it's still an analog. And this monotonicity along such a foliation suggests that some of this positive mass theorem, this local one, might be equivalent to the nonlinear stability of such spacetimes. And this is all what I wanted to say. Thank you for your attention. There are a couple of references I wanted to list at the end, and it's basically a summary of all the work that's been done. The first work here introduced this mass quantity. Second work discussed Ricci flow. Third work here established this positive mass in dimension 3. And the fourth article here is about this Hamiltonian formulation in the physics context. Thank you very much.
Okay, thank you very much, Klaus. Thank you for the informative talk. Are there any questions? You haven't mentioned the paper that appears today in arXiv, right?
Oh yeah, it's kind of an overview paper, so there are no new results. I didn't mention that. That's right. Well, I lost a couple of words in this overview article also on our mass quantity and how it fits in the general context of Ricci flow and scalar rigidity. That's right. So the arXiv number I don't know by heart, but you can look on the arXiv today. You will see this article as well.
Okay, any question? If not, we thank again, Klaus. Thank you very much, Klaus.
Thank you for inviting me.